we are going to figure out how to figure out and go through a process. Process meaning we can take any problem, divide it into little pieces, solve each piece one at a time, and come up with a solution. That is the problem-solving process. So we are doing a rock, paper, scissors game, also known as Roshambo in French. Has everybody played rock, paper, scissors? I never thought of that. All right, we have all played rock, paper, scissors in the class. So this is our first program with artificial intelligence in it. So the computer will perform the part of AI by picking a random move. So is that artificial intelligence? Yeah. At the very simplest, dumbest level, it's randomly picking something. And it's not based on your input. It's doing it on its own. So is that artificial intelligence? Yeah, it is. We want to solve the problem first. When we play the game, I go, and Sean does it, and I do this, and he does paper, and I say paper cuts rock, scissors cut paper, right? We do that without thinking about it, which I have to think about it because I haven't done this in years. How does a computer think about things?
Numbers or
And what we
true or
do,
false.
yeah, whether it's true or false, but what we did without breaking it into pieces is I chose scissors. Sean chose, just if you look at this, I chose scissors. Sean chose paper. How do we know whether we won or not? I win because the scissors cut paper. So are we doing this every time we play rock, paper, scissors or some other game? Yes. We're doing it because these decisions, we don't even have to think about. A computer doesn't think. It calculates. It's a big calculator. So it has to know the results of all of these decisions. And then if I do paper and the computer does paper, we have a tie. It has to know each piece. It needs to know all of this. So was there a sequence in how we made that decision? Sean and I cannot possibly at exactly the same time. It's never going to happen. It's always going to be a millisecond or something apart. So if I pick rock, computer picks rock, we tie. So is that a sequence of events? That means that we are making a decision here. I am making a decision. I'm going to choose, is that stone? No, that's paper.
Rock.
Is that
That's
rock?
rock.
Okay, paper is what, this?
Yeah.
Okay, yeah, boy. I'm gonna have to review my rock, paper, scissors stuff. Okay, so I pick rock. The computer randomly picks rock, paper, scissors. And then the computer has to compare what I did with its choices and then come up with one of these. So what kind of a statement in Python have we used to make those kind of decisions?
Yeah.
If. But the thing is, we're not just making one decision. We have to make one decision, then make another decision before we come up with the answer. Which is why this is called a decision matrix. So the decision statements will be nested per row. So if the player picks rock, we then look through and say, did the computer pick rock, paper, or scissors? Okay, well, if I did paper, we do the same thing. If I did scissors, we do the same thing. Different results each time. All right. So this is a good suggestion as to how to get input, because it's easy to compare numbers. This is not uncommon in real simple games. Is that oh crap, I gave you like the whole entire answer. I guess because I was had people that this could not make any sense. Well, I'm going to grab this part and then go down and grab this part. And yeah, I had to this has been modified over time. So you can paste that into yours. I'm just going to start from the beginning and do it once, because this is what I did to get to that point. So the first thing we need to have is input 1, 2, or 3. One rock, 2 paper, 3 scissors. Right? Whatever they type in, we want to convert it to an integer because integers are really easy to repair. I mean, to test. If we had the user type in rock, type in paper, type in scissors, that makes the game like really long. And if they misspell it, then it blows up. So this is better. And this just distinguishes and gives you a visual cue. I think I did it the other way around on the other one, but it doesn't matter. If you distinguish in your interface between the numbers and this, doesn't it look like you're supposed to type in 1, 2, or 3? So far, so good. This is kind of how I developed the program. I mean, I don't know how many years ago that was. We need to store that. So I think user choice is a good one. Does it have to be user choice? No. But it's my choice, user choice. Then in our sequence of events, because we're at this part right now, we're both making our play. We haven't made any decisions yet. We're at the point where, well, we need our randint library. Python has a library built in. So from random, import rand int. Because we need this guy to generate random integers. So this would be computer choice. Oh, now this should not be a computer choice. This should be AI, because like AI is all the big buzzwords now, right? Everything's AI. I have AI in my phone, in my car, in my shampoo. We want to return a random integer. And notice I just typed it in and I don't know what to put in there, but I paused right at this point and notice how it gives me some help. It says return a random integer in the range A through B, and it includes both endpoints. If you're computer science or you get another programming language, everybody's randomization works different. Sometimes it doesn't include the B, sometimes it does. In Python, if we do 1, 3, we get a random integer 1, 2, 3. That's what it means by including the endpoint, because this is the start, this is the end. So now we have a user choice, we have an AI choice. Doesn't that sound better than computer choice? Yeah. I'm going to market things and keep up. Owen raised his eyebrows at me. Okay, Owen, just keep it to yourself.
I was agreeing with you, but.
Oh, okay, it didn't come through as agreeing. It came through as, yeah, whatever, dude. Okay, no, it didn't.
I was like, yeah, makes sense.
Okay, yeah, it was, I was kidding. So now we go back up to our decision framework. Because all we've done is created these values. We are not even to the point where we're doing a decision matrix yet, are we? We're not, because we have to do everything one step at a time. We're at the point where I do scissors and Sean does rock. That's all we've done. It took us that much to make that play. Now we each look at what each other did and determine who won. But the computer can't just look at it. We have to tell it step by step what to do. So Sean said we should use an if statement, which is exactly right. So if user choice equals, what am I comparing my user choice as an integer? How would I find out that it's rock? What would I compare it to see if I chose rock? Because I typed in a 1. A 1, yes. I know it sounded like it was gonna be a trick question, but it wasn't. I don't know. I kind of didn't do that as well as I could have. Okay, so if the user choice is one, but when you look at our decision matrix, we know the next decision we have to make is what did the computer do? You can make this thing so complicated, you can't even figure out what's going on. What we're doing is breaking it apart. First, we decide the player, then we decide the computer. So inside of this, which is a nested if statement, perfectly fine, if AI choice equals one, we can just print it out right here if we want. I'm not going to do the whole, you'd pick this and you pick that. I'm just going to say, so if we both pick rock, what happens? It's a tie. Because bashing two rocks together doesn't win anything. You just have two bashed rocks. Well, we've got one decided. Maybe that's what the AI picked. How do we keep looking through these to see which one the computer picked? We have to make two other decisions. What do? How do we make more? It's not more than one decision. We have more than one right answer, might be a way to put it. What was that? Yep. Because the computer can't pick 1, 2, and 3. It can only pick one of those. So LF means, well, if it's not one, then it is 2. Which 2 is paper, so paper covers rock. I can remember that. Right? Now is it getting pretty simple? Now you have the pattern down? It is. Because this is our pattern for everything. Now at this point, we can go two different ways. We could do LF3 and be specific, which there's nothing wrong with that, so I think I will. But what other choices do we have at this point? We don't have any. All that's left over is 3.
Could you add another, instead of the elif, can you just add another if and then do an elif at the end?
Because we can't choose more than one at a time. We can either do 1, we can do 2, we can do 3. So this means it cannot be more than one answer. Is that what you're asking?
No, if you did, so you got. If your app choice, right, is 1, elif. Your app choice equals 2.
Right?
What if you just did another if for the app choice 2? And then elif app choice 3?
Then we're testing to see if the computer generated a 1 and a 2.
Oh,
Which means we're testing for 1. Oh, it's not 1. We test again for 2. So we're doing separate tests as if we could do both of them at once.
Okay.
So LF means it's like an exclusionary thing. It can only be one of these. It can't be anything else. So Python's designed to do this more efficiently. So here would be where you run into the problem. Why do I need to make a separate choice here? I could just do else or LF because I can't press 1 and 3 at the same time. So part of it's a logic thing. If I have radio buttons, and each of those radio buttons or check marks can be on or off independently, then I'd have to have 3 decisions separate. I can only have one choice. So I have to, it's either this or this or this. So think of it as or. Is a one way to think of it. Scissors, rock destroys scissors, right? Well, I don't know if that's how it goes, but we'll say that's how it goes. That. Now, we've got this, if the user choice equals this, if LF. What do you suppose the rest of this is going to look like? Does anybody see a pattern here? There's definitely a pattern here. I don't know why that's not down on the next line. But let's put it down there because they all belong together. There. There is a pattern here. We make this decision. Inside of this decision, we make this decision. We make this decision. Inside of that, we make that decision. So this is a really good example of nested ifs. So if I wanted to do this really quickly, I could, but let's do it slowly. Because L if user choice 2. So could I save some typing there? The only difference between this and this is my choice. Could I save some typing here? Is this going to be exactly the same, but with different results? It is, isn't it? Or do I have to change my decision for the next one? Part of programming is recognizing patterns. Do you think if I copied and paste line 8 through 13 into here, the only thing I'd have to change is the results? Do you think that would work? Owen's not doing anything. Everybody's just looking at me. Oh, Sean's shaking his head. Yep, you're right. Because the decision is exactly the same. Because we have to change this for the user. But every single time we have to do rock, paper, scissors, rock, paper, scissors, rock, paper, scissors. What changes is the result is different. So recognizing patterns is a really useful thing in programming, which also means, look at that. I can type out the whole thing. I don't enjoy typing. Well, I mean, I can type, but I was making a play on my we enjoy typing thing. Change that, change my results. I'm done. Do I have to have an LF here? No, just like I didn't before, but this makes it explicit and might be easier to understand in the code as you're looking down. You know that there's a 1 and a 2 and a 3. How about that? So I use the same process I've used for every program since the beginning of the semester. I use the same process when I'm trying to figure things out myself. However, when I'm trying to figure things out that I haven't figured out before, it does take me a little bit longer because I have to break it down just like this and figure out something one at a time. But that's what we did. We broke this down into first, let's make this decision. Next, let's make this decision. Next, let's do the outcome. We broke it into little pieces. You solve one thing at a time. Are we done with our program?
Gotta do that.
I didn't do all the output, but yeah, it should work. I'll pick one. Now, it's not going to make the right decisions because I didn't complete modifying the program. And I don't have all the output that's in my example, but you don't have to get everything right first time around. You could think of this as like a beta test, a beta program. And I did, I kind of developed it a little bit at a time. So if you sit down to code and you just start typing in code and want to try to solve the entire program at once, you can end up looking through all that code and trying to figure it out later. Normally what I would have done is I do this, I can just undo. I test one thing at a time. So I test to see, does this part work? Then I go on and I test to see, does this part work? And then I add something else and then I test that part. I test it as I go. I don't try to do the whole thing and then try to figure out the snarl of code afterwards, which is I've had to do that with people. But if you do it like this, well, do I really need to test this? No, we've done enough programming. We know that we can get a 1, 2, and 3. We've done enough that we know we get random integers. Really, this is where I would start testing. Right? After I've done this, I would see, okay, we don't know what the computer is going to come up with. I mean, we know what we are going to come up with. We know the computer is going to pick one of those 3, so I could have tested it at this point. I probably should have. We know that the only choice we can make is rock. There. So we try it again, and we know that's going to work. Then we just keep going and finish it. So break things apart into pieces. Don't try to solve everything at once. Start with the first thing you can solve. Start at the beginning with a little tiny part. I just took a look at the assignment, and one of my students is saying, at the top, it says use a loop, and she says, yeah, you should have done that right away. Well, I wanted to solve this part first. Is adding a loop into that? That can add an extra layer of complexity that I really don't want at this point. I want to just get this to work. And I don't know what happened to my other part. I had 3 of them in here at once and I deleted them all. Let's go back to here. Okay, so I've solved one problem. Am I trying to solve how to loop this and make this work at the same time? No. I do one thing at a time. I had forgotten I was even in here. So now I'm ready to solve the while loop because, why? Because this works. We know this works. Do we need to repeatedly get user choice, AI choice, and make our decision? Where do we place our while? That's what I'm asking. Where do we start our loop?
Before the if,
Do I make my loop here?
before the if.
Right. So if I do that, my loop is going to loop through making a decision. But I'm only going to enter user choice and AI choice once. So when you're playing multiple rounds of Roshambo, I will go. And Sean does his, and that's it. We keep making the same choices over and over again. No? I'm trying to lead you to the answer, not tell you what the answer is. What do you think, Sean? It's not, I can see by your eyes, it's not making sense.
After your user choice.
You do it after your user choice?
And you're after,
We want them to play the game multiple times. You look here,
I mean, you do it before. I'm talking
Right.
about your.
so you enter the choice, blah, blah, blah. Oh, I only put in 1 round. I need to do one where I can do more than 1 round, don't I? Okay. But yes, if you wanted to keep going, this is not a good, I should redo that with a 2 in there. All
At the
right,
top, up above the.
yes,
Okay.
because
That's
each time we want to play the game more than once. Maybe I should have started with that. I'm just gonna do a while true. So we want to play it more than once. How do I indicate to Python that all of this is inside that while loop?
Tab.
Yes. And if you select all the code you want to tab over, you don't have to tab over one thing at a time. It'll tab everything over all at once.
Mhm.
Because Visual Studio Code is designed as a programming environment. So if I want to move it this way, if I want to move it to the left, I use the Shift key. So I can quickly move it in any directions. Python is dependent on indentation or tabs to know what belongs with it. So this code is going to repeat over and over and over again. Well, I think I've solved that problem. I've got my while loop working. Now, if I had to also solve the while loop and do the input at the same time. Yep, paper covers rock. There. Ta-da. Look at how many times I can play. I can just keep going. Oh, why isn't, 4 is not a valid choice. Oh, there'd be an else. Wouldn't it? We were talking about why you'd use if and else and all that. Well, here's how I would use else for the user. I would say, because I typed in a 4 and nothing happened, enter 1 through 3. Right? So if I don't type in 1, 2, 3, I could put in a prompt in the else that says 1, 2, or 3. Because that's a part where, which I did, I typed in a 4 and I thought, okay, why is nothing coming back? Oh, well, that's because I typed in 4. We're assuming the users are typing in integers in this game. We're not testing for strings. We're not, strings that are not numbers. We're not testing for floats or anything like that. We're assuming the user's typing in integers. So far, so good. Oh, then I looked at the directions and the darn instructor put in The program will display the winner of each round along with the running score, which is like a running total. So if I'm playing Owen, I win one, he wins one. Right? The running score would be 1-1, which is just like football, basketball, anything else. Well, that means we need to do what? What do we need to do? And remember, I noticed I said starter to do, and I don't have any of that in here. So I'll have to figure that out. We worked on that when we introduced loops. We did a thing called a running total. So a running total is a variable that each time we go through this, we add something to it so it accumulates. Like if we start out with 1 the first time, if I win again, it's now 2. We want to do that outside of the loop so that it survives every loop through the loop. So I start out with 100. Okay. Maybe not. I could also, see, that's what happens when you program. Nobody knows that you've changed it. So I could make it, I could really win. I just make the AI start out with minus 111 points. Okay. We both start at 0. I'm going to have this be a legitimate game because I want to have a running total. I need to declare that outside of the loop because each time we go through this loop, all the variables that are used in here are thrown away. That's called scope, which means how long does this variable live? How long does this variable live? We put a value in here at this point. We get to the end of our loop. We start over. Everything starts over. It does not survive. We throw them away. We get new ones. Yes. All right. So we have our running total, running score, same thing. We're playing basketball. We want to keep track of how many points we have. Every time we throw in a basket, we don't want to have all the points thrown away that we just got. So how do we know if the player won? How do we know if the AI won? How do we know that? How does our decision structure determine who wins and who loses? Because ties do not count. Ties are for losers. No, ties are for, I don't know, people that work in an office. I don't know. So in here, with each of these choices, how do I know, well, between these two, obviously, how do I know if the player won or the AI won? Paper covers rock. Is that a winning combination? Yeah. So that means I won. Oh, I'm in the wrong place. So how do we increment a variable? Whoops. That's our shortcut way of doing it. If my player score started out at 0, now it's equal to 1. The next time it's going to be equal to 2, 3, 4, 5, 6, 7. Which means that at this point, AI score, if this, no, did I not call it AI score? Oh, I said choice. There. Oh, there's something weird that came in there. So that will increment each time. So to finish this out, what would I do? How would I finish out the program? I know all my answers are not right here, but just pretend they are. How would I finish out the program? Do I just keep track of who won on the first user choice and we don't care about the rest? How do I finish out this part of the program? What do I do?
Rings.
We would print that at the end, but I'm saying I put these two guys in here. How do I finish out user choice 2 and 3? How do I keep track of, for whatever decision I make as a user, whether I have one or the computer has one? Somebody's gonna say it. Do the same thing for both of those? Nobody's gonna say it. So if this is the winning one, I put in player plus equals 1. If this is the computer one, I put in player plus equals 2. We have to account for each time we win. Each time I win or each time the AI wins. I know my decisions are not right. Yes? Because each decision has a different result. So we can't just do it once because notice they're different each time. So here we'd have player plus equals 1. AI plus equals 1. AI plus equals 1, player equals 1. It's in a different part. So there's no way to really make this simpler because we have to tie it with the choice. When we go to here, now I've incremented my score. If the AI does rock, destroy, scissors, that score is incremented. Right? Yes? Okay, I'm losing everybody. Okay, so yes, as Hope said, you would print it, but you would not print it inside the loop. You would print your scores. Right there. Oh, why doesn't it like me? Oh. I don't know that that's it, but I really should do it right, but something else is wrong. Okay, just a moment. It's like gray, which means that it thinks it's never going to reach that.